Hey, thanks everybody. Appreciate it. Thanks for folks getting together. I was looking at the chat room. Sounds like we got a great group of folks with some good questions out there. Excited to get started. So first off, colleagues, welcome. Happy to be hosting today's panel on developing artificial intelligence in defense programs. I'd like to thank Vice Admiral Dave Lewis and the Acquisition Research Program and NPS, of course, for putting on this event and hosting us. And I think this will be an outstanding opportunity for all of us to learn, share best practices on this exciting topic of AI with its opportunities and challenges. We have a terrific panel of experts here today, and you know, as the moderator, I want to spend the most amount of time as we can with them because they're the experts and they could share the great work they've been doing. But I thought I'd set the table for just a couple of minutes with some thoughts from where I'm sitting with the team here at POC4I and NavWar. So if Michelle, if you could bring up that slide 2, which is titled POC4I and Space Systems and has that C&O plan. There you go. That's slide 2, the next one there. Perfect. So, hey, you know, as I was thinking about the discussion today and reading the great research done by my colleagues on the panel here, I started to think back as in my time as a computer science student and over my career. You know, I've always been just drawn to and fascinated by artificial intelligence, this notion of it. I'm a sci-fi book fan, you know, and it's obviously prolific there as well. And I think like many of us, the notion of the ability of these systems to be able to emulate human activities, cognition, and more so even be superior in it in some ways, has always, I think, captured the nation's attention, the world in many ways, as we've been on this journey. I was also a student of this topic and a fan. I've known we've been through many cycles of somewhat AI boom and bust, and it's talked about in many of our panelists' discussion as well, where there was this era of promise, and then systems not necessarily, the results not manifesting in what was expected. And I think that's consistent with many new technologies over the years and the trajectory of many new systems and capabilities out there. I think my sense is, and this is just Kurt in my perspective, I think we're at a different time now. I think these systems have consistently demonstrated a capacity to do things and approach challenges and analyze data in a way that wasn't necessarily possible. There's some wonderful discussions in many books, and of course our colleagues today that talk to this. But some of the big levers that changed this dynamic were, you know, significant quantities of machine-readable data and computing power, coupled with some terrific advances in the mathematics to be able to leverage those two to get outcomes we seek. You know, I think these are really exciting times, but there's a lot of challenges up ahead. And, you know, again, in the colleagues' paper and their talk, they'll speak to it. But there's an element of disruption in there, but there's also an element of not oversetting expectations beyond what we think the technology can deliver on. And so as acquirers, and folks who deliver capabilities that are sailors and Marines, and of course the other services, airmen and soldiers, and our Coast Guard colleagues as well, they need to be able to take into the field and be successful with. And so a lot of the discussion today will center on that. And so I'm really excited to talk to you all about it and to learn from our panelists. In the Navy, kind of dialing in a little bit to our neck of the woods here in POC4I and Space Systems, you know, obviously we're very much lined up with our C&O's navigation plan and our tri-service work between the Marines, Navy, and the Coast Guard and that grand strategy. And our CNOs focus really on sailors' readiness, capabilities, and capacity. And so as we as a PEO look at leveraging these technologies, and that's part of our job, is to take these emerging technologies and make sure we deliver them in the hands of our sailors and Marines before our potential adversaries have the ability to do it. We've been working along three main lines of effort, and they may not seem directly linked to AI, but they really, each one of them very much does so. And so, we're working on digitization across our organization. And that has both a home game and an away game aspect to the work. The home game part of it is really kind of speaks to changing the way we do business to acquire and deliver systems, leveraging AI and ML, whether that's a deeper understanding of our financial transactions, a deeper understanding of our engineering approaches, a deeper understanding of how we're accrediting and cyber vulnerabilities. You can start to see there's these digital value streams across many lines of effort, contracting, all of them. And our goal, leveraging AI and ML and these emerging capabilities, is to create this seamless digital flow of all of these value streams into one outcome-driven result, which is capability in the sailor and Marine's hands that they can then take to sea and be successful across a broad spectrum of threats. As we look towards, linked to that, as we look towards how we implement it, industry best practices in DevOps are a key integrating element for how we build both a development and a platform technology to enable these capabilities and to have them operate at the edge on really what is America's worst networking day. Our systems, as the part of the Department of Defense, is to be able to operate and be successful in extreme conditions that aren't necessarily those that our commercial sector folks may be thinking through. And so we have a unique opportunity and challenge as an organization to be able to deliver systems, these technologies, AI and ML technologies, in a way that they can be operated and successful in what is a very difficult networking or compute environment, a more harsh one, we like to say, at sea. But you can apply that to any one of the other services as they operate forward and away from garrison. We have a real focus as well on sailor self-sufficiency and really making our sailors and Marines the ops in our DevOps approach, and making sure that we're not giving them a gear that we haven't thought through enough to be able to, for them to successfully operate, and again, operate in a pretty contested environment. And so that is a lot of our thought process as we go forward. If you jump to the next slide, and this is my last one, and I'll start introducing the panel here. As you're thinking through the questions here for our esteemed panel, we talked a little bit about that linkage between artificial and DevOps. I don't see them as separate. Really, DevOps is the mechanism by which we have a development environment and then ultimately a production and operating environment that supports the rapid delivery of AI capability, whether, not to dive into some of the technology, but whether containerized or in another format, to be able to ensure that the systems, we can not only deliver them, but then rapidly update as we learn more from the platform and they operate those systems. Is that we think is a real key to success. We can't go out, deliver something once, walk away, and then come back 4 years later and say, hey, how did it do? This has to be a constant iterative process that matches the operational environment that the platforms are in. Yeah, that bullet on platforms and pipelines really speaks to the same thing, this notion of the target platform, compute platform, whether it's a ship, submarine, for us, aircraft or other platform, really needs to have a development pipeline that is optimized, leveraging commercial best practices to the maximum extent possible, but is dialed in for that specific operational use case that it's going to be employed. The quote there from Kai-Fu Lee, I very much enjoyed his book on AI superpowers, speaks to that data to learn by. I think in his book, he shared this notion that in the future, the outcomes we seek may be better derived from tinkering or learning quickly, given a certain set of assumptions, than more of the optimizing of a particular algorithm in kind of the lab. And so our sense is, that as we talked about earlier, data being a key ingredient to success, getting something out there and pulling data off our respective environments and understanding it and turning it and learning it from it are key ingredients. Sometimes we would spend a lot more time dialing in or optimizing an algorithm for a specific use case, and then wait till it's really at a high level of planned performance before we field it. And some of the colleagues talked to that a little bit in their papers, and so I'm excited for that. The last bullet there, that strategic high ground for our acquisitions. Again, as acquirers, one of our roles together is to think through what keys or what elements of this value stream, when it comes to AI and others, do we as a government want to maintain tighter control of? What do we work with industry on, whether it's the traditional defense sector partners we've had and been fortunate to work with for many years, or those commercial IT partners that maybe we don't have as established relations with, or the small business. And by owning key elements of that strategic high ground, we can drive affordability and also drive our ability to more rapidly pivot to meet requirements while bringing the best and brightest in industry to the table to help solve our problems. So with that, I'm going to now introduce our terrific panel here today, and then we'll get into their terrific discussions here. So first, I'd like to introduce Dr. Ying Zhao, is a research professor at the Naval Postgraduate School. Her research focuses on data sciences, machine learning, and artificial intelligence methods, including lexical links and link analysis, collaborative learning agents, and reinforcement learning of search, visualization, analysis for defense military applications. Since joining NPS, Dr. Zhao has been a principal investigator on 25 contracts awarded by the DoD. She also is a co-author of 4 U.S. patents in knowledge pattern search from network agents, data fusion, and visualizations from multiple anomaly detection systems. She has a PhD in mathematics from MIT and is the co-founder of Quantum Intelligence Incorporated. So welcome. If we were in the room, we'd all applaud, but we're in virtual, so here, I'll clap, and then we'll go to the next one. Dr. Timothy Shives works in information technology management at the Defense Manpower Data Center and is currently on special assignment to the Naval Postgraduate School's Information Sciences Department as part of the Defense Senior Leadership Defense Development Program. He is an officer in the United States Marine Corps, where he began his military career as an attack helicopter pilot flying AHIW Super Cobras, and has served more than 15 years across both active duty and reserve components, supporting a multitude of occupational specialties across fields in financial management, IT management, project management, acquisition management, and data management. He has a Doctor of Education in Educational Leadership, and Master of Science in Information Technology Management, a Master of Business Administration at NPS, and a Master of Arts in National Security Strategic Studies at the Naval War College there. He's also working on his second doctorate in Information Sciences, so welcome to Timothy. All right, and then I'll keep going here. Dr. Bonnie Johnson is a senior lecturer with the Systems Engineering Department at the Naval Postgraduate School. In this role, she leads research projects across the Office of Naval Research and the CNO's office, Army, Marine Corps sponsors focused on directed energy, laser weapon systems, automated battle management aids, artificial intelligence, predictive analysis, and complex system engineering. Prior to working at NPS, Dr. Johnson was a senior systems engineer with Northrop Grumman and SAIC, working on naval and joint air and missile defense systems. Dr. Johnson has earned a PhD in systems engineering from NPS, a Master of Science in System Engineering from Johns Hopkins, and a Bachelor of Science in Physics from Virginia Tech. Welcome. And of course, last but not least, Dr. Bruce Nagy is a senior scientist and systems engineer at the Naval Air Warfare Center Weapons Division at China Lake. His research focuses on advanced game theory, techniques, artificial intelligence, and machine learning applications as applied to naval weapon systems and tactical decision aids. A former engineering duty officer, earned a Master's of Science and Bachelor of Science in Electrical Engineering from NPS, and a Bachelor of Science in Biology and a Bachelor of Arts in Mathematics from the Citadel. He continues his research in neural networks with interest with postgraduate work in modeling brain stem activities and muscle fibers at UCLA in cooperation with the National Institute of Health. So welcome across the board. So hey, we'll jump into the panelists and I'll turn it over to them. I think first off, we'll have Timothy, who will provide us insight into his research on acquiring artificial intelligence systems and development challenges, implementation risks, and cost-benefit opportunities. So Timothy, take it away, sir.
All right, thank you, Adam. Thank you, sir. Good morning. My name is Tim Shives, and my talk today is on acquiring artificial intelligence, development challenges, implementation risks, and cost-benefit opportunities. While my colleagues are going to discuss their research that dives into more the technical side of artificial intelligence, I will do a brief introduction to the macro impact that the growing interest in AI has to its current impact upon society and the DoD. Utilizing the Web of Science comprehensive academic search engine, our study found over 300,000 scholarly publications on the topic of AI as of October 2020. The period of these publications covers the entire timeline from the inception of the term artificial intelligence in the early 1960s until present day. Using the VOS viewer, we created a network map that showed how AI, the term intelligence in this diagram, relates to other key topics, where each node depicts topics in excess of 10,000 articles. AI traces its roots to the mid-20th century, primarily to Norbert Wiener's concept of cybernetics, which he described as teaming between human and machine. It was during this period that the term artificial intelligence started to diverge from the larger field of cybernetics, and it became its own field of study at the Dartmouth Conference in 1956. Since its initial establishment, AI remained an area of scientific obscurity and limited political interest for over half a century. Today, with the rise of big data and improvements in computing power, AI has entered nearly every major field as depicted on this network topology. Thus, society has entered an era where AI can expand the capabilities of the military in data analytics, image recognition, human-machine teaming, and enhanced cyber warfare in both defensive and offensive cyber operations. And as part of the society, the DoD has been influenced by this rapid growth and interest in AI, particularly since the 2014 launch of the third offset strategy, which kicked off the Better Buying Power 3.0, which then Undersecretary Frank Kendall stated, focus on achieving a high payoff breakthroughs in areas such as artificial intelligence. Better Buying Power 3.0 noted that the fielding of new technology and advanced technology such as AI is a challenge for the DoD and the entire federal government. This is because current program management and acquisition methodologies have proven unsuccessful in meeting the task of providing requirements to the warfighter. And the recent case study of biometrics demonstrates that, quote, effective military innovation can only occur through an integrated approach that takes into account the interdependent elements of technology development, acquisition planning, doctrinal design, and warfare strategy. The Defense Science Board study on DoD's acquisition of software-intensive programs such as AI recommended that the DoD and its defense industrial base partners need to adopt continuous iterative development best practices. And in 2018, the DoD formed the JAIC, the Joint Artificial Intelligence Center, as a coordinating focal point between the Department of Defense for new technologies that fall under the umbrella of AI. But the JAIC is limited in its authority to coordinate and provide oversight to the numerous AI pilots and acquisitions across the DoD. In the 2020 Congressional Research Service report stated that the DoD may need to continue to adjust its acquisition process to account for the rapidly evolving technologies such as AI. And in a 2019 RAND report also noted that the DoD should utilize and adapt acquisition approaches that are, quote, appropriate for the technology. The bottom line is that the current processes and management control tools supporting acquisition do not provide the acquisition PMs with the ability to respond to issues in a timely manner, delaying the delivery of promised capabilities to the services. Thus, our study examined the strengths and weakness of several performance and project management methodologies available to the PMs: earned value management, EVM, knowledge value added, KVA, and integrated risk management, IRM. The first one, EVM. For those attending this webinar from the acquisition community, this slide depicting the EVM gold card should be very familiar to you. The federal acquisition regulations specify that DoD acquisition programs whose contracts value exceed $20 million are required to use EVM in their program office. It is also the method that is recommended by the Project Management Body of Knowledge, the PMBOK. EVM is a system that PMs use to integrate work scope with the cost and schedule of that program to improve control and planning of the acquisition. It establishes a baseline for the objectives of the program to measure cost and schedule performance while the project is being executed. In essence, EVM provides an assessment of actual physical work a project has completed compared to the baseline. When properly employed, EVM provides a reliable prediction of the total cost schedule requirements for a project through 3 distinct dimensions: the planned value, the earned value, and actual cost. Knowledge value added. KVA is an objective quantifiable method used to measure the value produced by a system and the sub-processes within the system. It was originally developed by Dr. Housel and Ganevsky to assist business process reengineering, and KVA provides an objective quantifiable methodology to measure the value of a process or service. In essence, KVA performs a single function describing all processes, outputs, and common units. It allows managers to compare the efficiency of various steps across all processes within a common value reference point. The term value has a different meaning in KVA than it does in other methodologies such as EVM or IRM. KVA bases its definition on complexity theory that views organizational process by their ability to change the input into common units outputs as depicted on this slide and the steps. And unlike any other methodology, KVA assigns these common unit values to both the processes and the sub-processes rather than the firm as a whole, which provides more data than cost alone that the PM can use. Integrated risk management. IRM is a system that was developed by Dr. Jonathan Munn to provide management the ability to analyze risks associated with development of new project or initiative. It combines several commonly accepted analytical procedures such as predictive modeling, Monte Carlo simulation, real option value, portfolio optimization into a single comprehensive methodology. And it comprises 8 distinct phases of a successful and comprehensive risk analysis implementation, which are qualitative management screening, forecasting, predictive modeling, base case static modeling, Monte Carlo risk simulation, real options problem framing, real options value and modeling, and portfolio resource optimization, reporting and presenting the updated analysis. So let's compare the methods. Choosing a methodology depends on the nature of the project, the commitment from the organization, and the desire to align strategic goals with the project, predictive capability of the methodology, the flexibility required, and the time and knowledge available to the PM. EVM only needs the management team to track the cost and schedule of a project compared to the baseline, as there's no goal alignment with the organization. So if the software is not complex or consists of known process, EVM is sufficient to monitor project. However, KVA can provide an objective ratio scale measure of value and cost for each core process within its subsystem with any IS system, including those with artificial intelligence. Integrated risk management requires organizational leadership, portfolio, and project managers and the analysts to determine how the project fits within organization portfolios and the uncertainties of the project estimates and potential strategic options. So combining KVA with the results of IRM allows managers to generate the value of the system, risk uncertainty, while also providing strategic real options analysis through Monte Carlo simulation and other techniques. And this can be in conjunction with earned value management to meet the DoD requirements while simultaneously providing a more robust project management tool. So combinations of EVA, EVM, KVA, and IRM. So as stated previously, EVM remains the only program management methodology required by the U.S. government for contracts exceeding $20 million. However, there are significant limitations for EVM and AI acquisitions. The major weakness that it was not designed for managing AI acquisitions that follow iterative pathways. To remedy it, we can combine it with EVM with KVA and IRM. An example is during the requirements phase of EVM, with this combination can ensure that a given AI acquisition is aligned with the organizational strategy and that a baseline process model has been developed for establishing current performance before acquisition of the supporting AI. In summary, the growth of interest in AI is on the rise. The DoD acquisition community is not optimally postured for effectively assessing the performance and the development of their AI programs. While earned value management remains the only program management methodology required by the U.S. government for all DoD acquisition programs, PMs can augment EVM with other methodologies such as KVA and IRM. And I know I went very quickly, but if you have any questions or comments, please use the chat box during this webinar, or we can discuss after the final presentation by Dr. Ying Zhao. Last but not least, I'd like to thank my co-authors and the two graduate students, researchers. And I thank you for attending this webinar, and I know that you look forward to the next presentation by Dr. Bonnie Johnson.
Hi, my name is Dr. Bonnie Johnson, and I work for the Naval Postgraduate School in the Systems Engineering Department. And today I'm going to talk about artificial intelligence systems and unique challenges for defense applications. So there are four main categories of challenges for the Department of Defense as we start to develop AI and machine learning systems. So one of the big challenges, first of all, is that the decision domain in the Department of Defense, especially for tactical decisions, but also for mission planning and strategic decisions, is highly complex and oftentimes can result in life or death consequences of those decisions. And there's also a complex interaction between human warfighters or human operators or human planners and those automated decision aids. Another big problem for machine learning systems in particular, and I'm going to talk about that a little later, is that a lot of data is required to train and develop these systems. And sometimes in the military domain, data can be hard to come by. One of the issues could be that we might have to overcome data classification hurdles. We also have to worry about by just the action of collecting data that we might be presenting new cyber vulnerabilities. It can also be very costly and take a lot of time to gather this data, to either, in some cases, simulate it, to maybe go out and conduct fleet exercises or war games with specific data gathering things in mind. Another big factor, this is for basically engineering AI and ML systems of all kinds, is that these are new types of systems that are slightly different than traditional systems that we're used to engineering. So there may be new methods and particular parts of the systems engineering process cycle, and also for acquisition, that may need to change, or that we may need to pay particular attention to, especially new types of defining requirements for systems that learn and are implemented differently in operations. And also we need to pay particular attention to validating and evaluating these systems and making sure that they're ready for operations. Also, for defense applications, we're always concerned with our adversaries. In one sense, many peer competitor nations are also developing artificial intelligence. So it's almost a competition to see, can our AI systems keep up with peer competitor AI systems? Also, the more we automate systems, the more we introduce automated decision aids into operations, the more we open ourselves up to cyber vulnerabilities. We always have to be mindful of that threat, as well as the fact that AI and ML advances in general can create new threats that we have to keep in mind. So first, I want to just quickly say that there are many definitions of artificial intelligence out there, but when I use that phrase, I'm going to use it kind of broadly and generically and simply to mean that AI is the application of human or biological processes to solve problems using machines, and I'll be really talking about computers being able to do those applications and solve those problems. I like this simple Venn diagram where we can imagine, a large set of all of the automated processes that exist, and within that larger, set of automated processes, we have the set of artificial intelligence processes, and then within that, we have machine learning systems. And the remainder of my slides today are going to be mainly focused on machine learning systems. The thing that really separates machine learning systems from other primary types of AI systems is that traditionally we're used to explicitly programmed systems where there's some kind of if-then process to it. If we input this kind of information, we expect this kind of output. So we're really talking about deterministic systems, whereas systems that learn from data, machine learning systems, really they are trained and they are really products of the process of training them using the training data sets. These systems, again, are different than these explicitly programmed traditional types of AI systems. So this chart shows this a little bit more clearly. Across the top of the screen, I have a very generic systems engineering and acquisition lifecycle. Okay, so the first half of this left-hand screen, the blue part, is all of the things that might happen pre-deployment. The design, development, test evaluation, all of that good stuff. And then the green part is post-deployment. So now we've deployed this perhaps machine learning system, and now we are operating and sustaining it. So for a machine learning system, during this pre-development phase, basically we're gathering up a lot of data, we're pre-processing that data, and then we're using these learning techniques, to develop this model. Okay, so this model basically is a product of this process of training it on data sets. And this becomes our machine learning system, okay? And then when we deploy it in operations, now we are inputting real-time data or operational data. We may pre-process a little bit, but we're basically inputting operational data into this model that we trained that's been developed, and it is outputting some kind of prediction that could support some kind of decision. So it's acting as some kind of decision aid. So some of the characteristics of ML systems include, and this is probably the key one today, is this characteristic that these systems are non-deterministic. Their behavior during operations can lead to variable results. And the fact that many of these machine learning systems are complex causes even more variability or, unexpected behavior to emerge from these systems. Another key point, though, especially as we think of how these systems are developed, is their intimate connection to data. First, they are intimately connected to the training data set that they're trained on. So they're only going to be as good at this point, once it's been developed, based on how good the data was. So they are a product of this data training process, and they are wholly dependent on their training data. But then they also become continue to be dependent on the operational or the contextual information during operations. And so if they happen to find themselves in a very complex operational situation, again, that's going to affect their predictions. If the real-time operational data that they encounter is very uncertain, then that's going to lead to very uncertain predictions. So this leads us to lots of different failure modes of AI ML systems. And this list of failure modes here, or this picture of failure modes, is not complete. Basically, it's just a first look. And the bottom line is that the failure is that the prediction outcomes of this model will be wrong. And they could be wrong due to problems with the data, problems with the operator interactions, uncertainty in the data, problems with adversaries, and on and on. And now we look at what are the root causes of these failure modes. So if we look at, and I categorize them based on, you know, what root causes were caused during the pre-deployment phase, and which root causes or failure modes are happening because of things that are happening during operations. And so the bottom line is that most of the pre-deployment problems are going to be problems with that data: bias, incompleteness, corruption, mislabeling, poor validation methods. Also not really, you know, another problem is problems with the algorithm that is developed itself. So maybe we've chosen the wrong algorithmic approach, for example. And then similarly in operations, again, we could run into problems with the operational data. We could run into a problem where the model was overfit. It was trained well, but didn't work on the operational data. Operational operator issues where the operator doesn't trust it or doesn't have explainability, or they induce error. And of course, again, there's adversarial problems. So as we look at solution strategies, step number one is to categorize our ML system based on its application. So is the set of decisions that it's supporting, are they a set of decisions that have consequential decisions that have profound effects on people's lives? In that case, safety is paramount. Or are they for an application where safety is less important? You know, are they a system that's going to just decide what advertisement to show in somebody's internet feed? I think most defense applications are probably going to be type A. There could be maybe some logistics or different applications where time is on your side, it's ample, where there could be some that fit into this type B category. So once we've decided that safety is critical, what are some solution strategies that we can implement to make sure that these are safe? So again, I categorize them according to, you know, which of these solution strategies can we do or need to be done during the design phase. And then I have this one where we do procedural safeguards that could be conducted during operations. But basically, we want to ensure an inherently safe design. We want to build in safety reserves. And this really gets back to making sure we have adequate time to do our training and our validation, and making sure we're really validating our training sets. Also to design in safe fail mechanisms. So we're going to allow, you know, systems to go into a manual mode or alert a human operator if we expect some kind of issue. And also make sure our systems are as explainable and understandable and trustworthy as possible. So really quickly, I have a lot of research going on to support this exciting area. I have students that are studying mapping different AI and machine learning methods to the tactical kill chain. I've got a student who's studying how to engineer trust into an AI system. I've got a group of students that has been studying what are the data needs of naval AI and ML developers, and can we come up with a data management strategy that gets that verifies that data and gets that data set to those developers. And then I have a new team that's now doing a deep dive into the AI system safety modes, and they're going to be specifically looking at air and missile defense use cases. And finally, I do a lot of laser research, laser weapon systems. So I've been working with some students and other faculty to develop an automated decision aid to support laser weapon decisions. And specifically, I highlight 3 areas where we've been looking at machine learning to kind of help determine the dwell time of the laser depending on the material composition of the threats, also depending on the atmospheric conditions, and also we're looking at using ML to prioritize threats if we're faced with a UAV swarm. So in conclusion, there are many applications in defense for AI ML systems. However, they are different than traditional systems, so we need to be mindful of their new challenges and failure modes and new methods for engineering these systems and acquiring them. So there are a lot of exciting research opportunities, AI, ML applications for defense, and the systems engineering of these systems, and I welcome collaboration. Thank you very much.
Welcome to my presentation. My name is Bruce Nagy. It is a pleasure to be sharing this research with you, and I hope you find it worthy of your time. This paper is about providing measurements specific to supporting AI development. The goal of the measurements is to support the acquisition community in having increased confidence that the behavior of the performance of the AI deployed systems will meet or exceed expectations. The motivation for this research originated from the Naval Ordnance Safety and Security activity known as NOSA and their concern about the garbage in and garbage out phenomena when training machine learned systems. That array of weights for machine learning process in the middle of the slide is a typical example of what gets deployed in an AI embedded system. Do we have confidence in that algorithm's functional performance when deployed based on those weights? Let me say it another way. Do we have confidence in those numbers? And an important factor in answering this question is based on whether the quality and quantity of the training set that developed those numbers accurately represents the operational environment in which the algorithm is going to be deployed. We face a real training conundrum. It involves the challenges caused by the limited amount of real data we have, and therefore how we are forced to focus on creating synthetic data, sometimes known as fake data, as our training set for our machine learned algorithms. Quick story, two sailors go walking into a bar. Oops, you probably heard that story, but what you might not have heard, and is much less funny, was described in an article in Fortune magazine last year about an autonomous car manufacturer that had its vehicles involved with 18 accidents in a 20-month period. Think about that, 18 accidents in a 20-month period. Another interesting fact, the company that had all the accidents refused to participate in a safety first initiative with other major car manufacturers. Did it financially hurt that company? What do you think? Well, they were recently awarded $3 billion to keep developing. I guess it didn't hurt them. What is the moral of the story? We, the Department of Defense, need to keep developing. There's no doubt about that. We are in a race and we need to win, but we absolutely need to avoid 18 accidents in a 20-month period. We don't have that luxury. When expensive missiles have an accident, that casualty can be very high. You cannot compare the commercial world with us. We have a much harder problem. Let's talk about that problem called synthetic data. In our research, we call this diagram our Mona Lisa because it accurately describes the challenges of creating realistic synthetic data for modeling and simulation. The modelers need foresight or operational SMEs, and even then, it's an educated guess, right? The brown side on the right needs to create the training data for the algorithms. The blue side on the left is what the machine learned algorithms will experience during deployment. The challenge is that the brown side on the right needs to accurately replicate Murphy's Law that might occur on the blue side. Does anyone have a crystal ball? The brown side needs to model and simulate with realistic accuracy the training data for the algorithm. This obviously is a tough and challenging job. Yes, this will be a technical presentation, and you might want to return to that joke regarding the two sailors. No such luck. So here we go. I developed two measurements, one for quality to assess the composition of the training data, and the other assesses the quantity or the size of the training data set. Please prepare yourself to see numbers and a little math here and there, as well as graphs. I'm not going to go into full detail, but I do recommend reading the 22-page paper I authored. The paper includes 2.5 pages of references that you might find worthy of your time to review and investigate. The paper includes discussions about ethics, law, and even an analogy to the nuclear arms race, as well as details about these measurements. The training set alignment test, also known as TSAT, is a rigor that begins the alignment between the operational real world and the modeling and simulation world. In effect, blue congruency with brown in the previous slide. The first part is a need to operationally define the order of importance, which attributes are the most to least important for that class to functionally perform. Once that is defined, it makes it easier to group the attributes into various grouping orders. Once the simulation generates the training set, then TSAT helps determine the order of importance based on the number of occurrences per class. This allows us to determine how well what was operationally defined as important is aligned to what was created from the simulation results. During the calculations, we provide a percentage of how operational needs match the simulation. As a rule of thumb, if your number is below an acceptable operational threshold, the default being 50%, then a new data set should be generated for that class. In other words, the data set for that class would be considered unacceptable. Notice that for the load truck class, there were only 10 attributes out of the 17 that were used, half primary and the other half secondary. Also, although we rank those 10 during the DOE process, we are only analyzing the first 5 to get a score. It really depends on your concerns and operational needs. In our example, the load truck class matched to 80%, and that visually looked about right. This star-N matrix is based on our sandbox development environment. We had 5 classes and we calculated where these classes would be plotted based on the XY axis. The x-axis is percent number of primary attributes versus total attributes for class, and the y-axis is percent number of primary attribute instances, those are samples, versus all instances for the class. The color scheme shown is a default, but can be color customized to support your operational and development goals. The color represents rigor in justifying where the plot for each class resides. In our case, there were 5 classes that we plotted. If the developer cannot adequately create a justification equivalent to the color code of the matrix shown below, then your training set should be rejected, meaning it's not enough quantity of the right data to meet operational needs. Understand that this matrix must apply to every class and, if needed, every attribute order grouping. When doing the star-N calculation, there are 5 steps to follow as listed. The plotting involves a basic calculation of ratios. Here are some visual views of both TSAT and star-N. See how the bars on TSAT have about the same height. That's attribute alignment. And now star-N starts to make a little more sense as well when looking at it visually, lower bottom, compare the 2 axes, left and right pie charts. We see that on the right there is an equal number of primary and secondary attributes, but on the left we look at samples or instances of the data and see that the primary had a greater focus. That makes sense. We are focusing on more important data. What if the opposite and the secondary had a greater focus? Why would you spend more time simulating less important attributes? If you did, you should reject the training data as being insufficient in terms of quantity of the right type of data to meet operational needs. Some thoughts from my group suggest that when one class is rejected, all classes should be rejected. It all depends. It is certainly important that you don't create a majority-minority class situation. It's also important that the algorithm have equivalently high success rates in recognizing all classes. Here are some obvious issues where the training set would be considered insufficient to meet operational needs. In TSAT, the alignment number is shown to be too low. That means the quality is very poor. In star-N, there are several issues. For example, what happened to the tertiary grouping order of attributes when it came to simulating it? They're not there. Why was there an equal simulation of primary and secondary order attributes? Are all the attributes within the grouping of equal importance? If so, why make a distinction? We now come back around to the beginning of our presentation and discussion, but hopefully with greater insights into how our description of TSAT and star-N measurements provides some thought regarding how training data is composed and how simulation results need to represent importance of the attributes your algorithm is being trained to use. I hope that you gain insights and a few techniques to consider to gain a more factual understanding of the quality and the quantity of a synthetically produced training set. Here are some of the related references I used in my paper for you to consider. Again, I recommend reading the full paper. It is certainly loaded with interesting information about AI development and its challenges. I want to conclude by stating my gratitude for your attention during this presentation. I very much appreciate it and look forward to answering any questions you might have.
Hi, my name is Ying Zhao. I'm a research professor at Navy Postgraduate School. The title of my talk is Leverage Artificial Intelligence to Learn, Optimize, and Wargame for Navy Ships. My co-author are from various of Navy organizations and Marine and universities. So leverage AI to learn, optimize, and wargame for Navy ships. This is based on current challenges and needs from Marine and Navy. Those organizations, their work is based on their operation concept. For example, Navy may be based on this distributed marine operations, and Marine may be based on expeditionary advanced-based operations. So those operations require capabilities, manpower, and logistics, and supplies, and so on. So meanwhile, there are many sensors and business process also collecting big data for downstream of readiness components for Navy and Marine to operate. So those are not just logistics, but they may be involved deployment, finance, support, various of decision components. So all this needs analytics in some level. So LILO is trying to focus on the three pillars of or three aspects of analytics, deep analytics. So when there are data from various sources, so we need data mining, machine learning, and predictive algorithms. That's one perspective. Since there are many business process, so optimization techniques are very important. Meanwhile, there's a unique perspective of military applications is when sometimes you don't have data. So your adversary maybe hide the intent or the new situations that's just the unknown. So in the no data situation, you may need simulation war game to actually generating data. Now, I'm going to show a few use cases that start to use the LILO concept. So first case is about marine maintenance and supply system. So this is a use case that I started last year to be able to actually show the feasibility of all aspects of LILO. So that's I put it here as the use case one. So this is really start with a lot of data. Specifically, let's say this is equipment about land armed vehicle. That is a important equipment for Marine. So they have a few years data pulled out from this GCSSC-MC database. This has covered many aspects of the business. Basically, this is equipment, so if they have failures and trouble, they send it to different locations to repair. And then if they're not repairable, they could be replaced and so on. So this whole cycle takes some time, and sometimes they could deadline the mission, which means they are very critical parts that needs to be fixed. Otherwise, the mission cannot be complete. So from this decision to deadline, they usually have an average time, let's say 32 days. So the idea is, you're trying to reduce this date as low as possible to reflect it, you're ready or not. So if you have a quick, fixing day, then you basically have a more ready. So that's how they measure actually. So we use predictive models to predict, what kind of ticket may have this particular deadline to close are larger than 32 days. You're bad, you're longer than average. So they're trying to optimize and fix that. So there will be more aligned to the average or reduce the average altogether. So predictive models are used. So we use the Orange, which is a typical Python package and has a visual flow for predictive models. And I also added the SOAR reinforcement learning outside the Orange. And we use lexical link analysis to try to look at the relationship between those decisions and the relationship between the items. And more important, we actually go through the whole process of this war game process. So basically, there's about 500 variables in this whole supply and maintenance chain. So we divided some variables in terms of attacker variables. So that's those are the variables that you probably cannot control. It's like a test or problem presented to the logistic problem. For example, miles and hours and locations of the users, so you probably cannot control. And sometimes the financial situation you cannot control. And then the other side will be called the defenders. And the defenders will be the ones that you probably can control, like which shop you send it to and how many spare parts and so on. So this and manpower. So basically, you can control some decisions. That will be your defender. So how do you solving that problem with the solutions will be two players in this war game. So we set up this two. So they're kind of asymmetric. So the attackers has a goal and they pull it into two different directions. And this co-evolution algorithm, which is a genetic algorithms, that's sort of set up in this opposite direction. So there's an attacker, there's a defenders, they pull in different directions. And this algorithm was developed at MIT AI lab, and they used for the cyber attacker defender situation. And we use them to for the logistic problem, and it's very interesting and successful. So here shows a visualization of this algorithm actually in operation. So the attacker and defender, remember, they're the variables that we set up for this process, and they can vary, just sort of simulate, to see what kind of attacker or what kind of logistic hard problem out there. So the evolution means they can evolve in each generation to create a difficult problem. So in this case, the attacker actually can evolve from existing database to a much difficult, higher fitness problems. But however, the defender, which means, if you actually can have solutions that can handle those difficult problems, they also evolve, but in this case, they probably cannot find something better than what they have already. So this is a summary. It says attacker each generation get more fit and gets harder, and the defender, which is the solutions, are not really gets better. So you think this might be a vulnerabilities in this systems using this perspective. So you'll be able to looking at the vulnerabilities, maybe evolve the solutions accordingly. So, but then we could argue that your problem may be too hard because you don't apply this constraints on the line. So sometimes, for example, you cannot have two kinds of defects at the same time, right? So things like that, where pandemics just happen, with a certain probability. So adding that kind of constraints will be something called grammar that for the co-evolution algorithm to take out. So that's our next step. That maybe makes the defender look better and not necessarily getting worse every generation. The The second use case is partial use of the LILO as a lexical link analysis specifically for this product, which has already existed for Navy System Command. So they're interesting to predict the parts of failure during the ship deployment. Okay, so it's out there in the deployment, what parts will be failed. So if you can predict it accurately, so you can acting proactively doing maintenance to do predictive maintenance or prepare more spare parts. So that's the purpose of this product. So they based on the traditional theory of probability of failure and so on. So they already have a model that does the prediction. So we apply the lexical link analysis. Basically says, you can have different information if you look at what kind of items are failing together historically across the ship and based across the ship, of course, the same hull type and so on to see if we can improve the probability of to predict the probability of failure. Indeed, we can, and we improve quite a bit on the two tests that we've done, something like from 60% to 80% of the accuracy. Another use case right now, we just started and haven't really have positive results yet. Basically trying to use this lexical link analysis idea to try to sort out the items that you don't have money to buy for some reason. So underfunded ships sometimes have items they don't have money to buy, then they will put on this financially restricted work queue. So that the task is how to prioritize those items so you can fundraise and maybe buy those items for them. So this is just trying to to see what kind of method, maybe lexical link analysis, sort of computing this network of items, and then we can use a centrality to sort out the most important items. But however, we haven't got positive results yet. We're still in the process to comparing with their baseline. So in conclusion, so we showed a LILO framework provide a predictive and simulation platform for the Navy ships. SOAR algorithms and coevolution algorithms can be integrated to looking for the vulnerabilities of a long value chain and look for solutions which maybe provide a resilience accordingly. And we recommended maybe apply more of those deep analytics for Navy ships, collecting the right data, collecting the feedback data for machine learning if possible, and looking at the whole spectrum of this logistic chain. And we'd like to thank for Navy Postgraduate School, Navy Research Program for supporting an ONR Neptune program for support, and the encouragement to do technology transfer beyond the research period. The view of this presentation is the authors and do not reflect the U.S. government or U.S. Navy and their component. Thank you.
That was terrific. Thanks so much. I know, first, what a great set of discussions so far. Wonderful dive into various aspects of artificial intelligence. Much appreciated. I know we only have a few minutes left, so I thought I'd ask each one of the panelists to share their thoughts on a question. I've kind of going through the chat, and there's been a really robust discussion in there, which is fantastic. I kind of pulled together one question, and I'll ask each of the panelists to give their thoughts quickly on it. The question is, industry advances in AI in a matter of days and months. The DoD obviously takes longer in a lot of aspects. what are some things that as acquirers of systems we should change in our processes to better accelerate and pace that threat? And so I'll, Tim, if you don't mind, I'll throw that one out to you first, and then we'll move down the line from the order before. So question there on AI and pacing the threat and what things we need to do, or opportunities, what things we need to do to be able to, maybe some governance or other roadblock to be removed so that we can meet that challenge. Over to you.
Sure. Yeah. And I believe that's a take on Matthias's question, which I wrote the paragraph, so I believe I put in the chat. But basically, when you look at the DoD challenges with acquisition, especially of new iterative technology, emerging technology, it's the phrase, you know, Rome wasn't built in a day. You know, as a ship driver, you know, so you can't turn ships quickly. And we are organizationally, we're a machine bureaucracy, so we can't make those rapid changes quickly. But what we can do is do it iteratively. And I think a lot of the last decade, you've seen a lot of good leadership initiatives, starting with third offset, better buying 3. And you brought up Admiral Gilday's slides up there. I mean, those are all great things that we move. So it's incremental. So it's kind of like the, you know, act locally, think globally. Well, that's how we have to do in the DoD too. You got to make incremental changes across the board. But I think there was one that Matthias talked about with DevSecOps. I think Kessel Run in the Air Force and the DoD Platform One has really done great work in those areas, speeding up our development cycles, as well as the Defense Innovation Unit. And it kind of ties into a question I was in the process of responding to Robert. They do a lot of goodness there with dual use technology, where especially like that the commercial sector has developed. They found application for it in the Department of Defense.
Great, great thoughts there. And I've had the opportunity to see all the services are really doing terrific work across the board. Bonnie, you want to take a crack at that one? Some thoughts from your perspective?
Sure, and I will answer this from a systems engineering perspective. So that is part of improving and speeding up the acquisition cycle. But I think that there can be a lot of things done during the pre-deployment phase. I think just by understanding what the challenges are operationally and what the safety failure modes could be, and then making sure that we have, you know, as fast but also as safely as possible to validate these systems. One of my student teams is currently working on a data management strategy for the Navy, and they've gone out and interviewed a lot of different people in a lot of different missions. They've been looking at battle readiness, kind of tactical. They've been looking at information security, so AI applications for that. And then they've also been looking at the logistics mission. And they're finding that in some cases, a lot of data that could be useful to AI ML developers is simply not saved. And that's largely true on operational ships, because for many decades, we didn't know that that data could be valuable and would be valuable to AI ML developers. So they've been looking at a system for at least speeding up the process of getting good training data sets to train these machine learning and other AI algorithms. So I think part of it are strategies to get data to the right people in the right way that are valid, so we can, you know, at least speed up the R&D process. So thank you.
Wonderful thoughts, Bonnie. Bruce, your thoughts?
My thoughts are repository. I think that, and it's similar to what Bonnie's saying. Actually, I'm trying to support Bonnie in this, and one of her capstones is that I think we need a repository of the right quality and quantity of training data. And if we have it, we can almost immediately march out and develop our algorithms. I think one of the biggest problems is that we have a curation issue with getting enough data available to really do what we need to do. And I think it slows down a lot of folks. So I put in several proposals to look at doing a repository specific to tactical data and decision aid support. And so I've gone out to Navy War College, looking at Navy War College tactical data. When Bonnie talks about a lot of data being dropped, a lot of data gets dropped from Navy War College. Tactical Group Pacific by you has some great data. So there's a lot of really fine data out there that we're not taking advantage of. And I think if we had that data and we incorporated it, we massaged it properly, we can much more rapidly develop our tactical data aid support systems to get out to the fleet sooner.
That's great. Thanks. Compelling idea there on a mega repository, so to speak. Wonderful. And Ying, any thoughts from your perspective on how we pace that challenge?
So I think we could leverage more collaboration with academia and industry. So I think somehow DoD has to, so we're unique because we have the security requirements, this complexity, but somehow you need to kind of introduce this problem to industry, to academia, and have them to help us and through various programs, SBIR, Navy Acts, or whatever funding mechanism. I think one area is like in commercial area, they have like Google or Amazon, they have like a lot of funding to support research and products, but on the other side, the DoD may be falling behind because the funding issue, and also the way to communicate our needs, our unique challenging. You know, the students out there, they want a challenging problem, and you should come to DoD. Like somehow we should support them to actually help us to speed up. So that's my thoughts.
Great. Well, hey, everyone, first a virtual round of applause for all of our colleagues in the panel. Well done. It's been a true pleasure for me. Great dialogue on the chat, and the Navy, Nation, and the whole Department of Defense are very fortunate to have patriots like you working hard on these systems, and look forward to a continued dialogue and the hard work up at the Naval Postgraduate School and other stations. So thanks again, folks. Again, thanks to the NPS team and that put this all together. Well done. Out here from San Diego.